Hello, everyone. I am excited to talk to you today about a topic that I'm very passionate about due to its exciting applications in earth science and modern society, and that is satellite data collected with not only satellites, but unmanned aerial vehicles, airplanes, drones, mobile devices, and we'll also talk about GPS data. So, a quick reminder to start us off. All satellite images collected consist of raster data, right? One of the two fundamental types of geospatial and GIS data. Raster data is essentially grids of numbers or pixels. They are derived from a grid-based coordinate system of contiguous cells. The spatial resolution refers to the real-world length units of one of those cells. And the way that I like to remember the difference between raster and vector data is raster literally means screen in Latin. Now, just a quick double click on raster data. These are images. These are grids of numbers. These are things with pixels. So if it's pixelated, if it's a photo, if it's a digital image, it's a raster. And I mentioned the spatial resolution. It's basically the size of one side of one pixel. So consider these three raster data sets shown in A, B, and C. You will see that the example shown in A has the lowest spatial resolution of about 100 meters. We increase the spatial resolution by a factor of 2 in B. So we have a 50-meter spatial resolution, but keep in mind that we have increased the number of cells by a factor of 4, since we improve the spatial resolution in both the X dimension and the Y dimension, right? So improving the resolution in both of those dimensions means that we improve it by a factor of 4, since the resolution gets twice as good in both the X and the Y dimensions. And in fact, we can go ahead and consider an even higher spatial resolution image shown in C. And again, that has 4 times more cells or pixels than the image shown in B. So spatial resolution, the real world length units that correspond to pixels in an image. Now, remote sensing, probably a topic you've heard before, maybe in our class. What does it mean? Remote sensing is simply the science of obtaining information about objects or areas from a distance. And you can, see this satellite is maybe collecting some of that information about objects or areas from a distance, but we actually have some pretty sophisticated remote sensing hardware and software ourselves, right? In our eyes and our brains. Our eyes and brains are very good at looking at things, objects, or areas from a distance and processing information out of them. For instance, we know that cars and trucks and so on move, right? We know the speeds at which they should move. We can catch things like a football or a basketball out of the air because we can predict the trajectory using what we know about the physics of the world. We can sense colors. Our eyes and brains are frankly quite amazing remote sensing devices. But we also can put some of these sensing devices on satellites, on airplanes, on drones, and even on phones. And so when we talk about remote sensing, those are kind of the platforms, the data acquisition platforms that we think about that are capable of acquiring remote sensing data. And importantly, we need geographic information systems to unlock the power of remote sensing data. You really need to understand things like coordinate systems, projections, spatial resolution, and so on in order to leverage this data to solve real problems. So the fundamental kind of ground floor of remote sensing analysis starts with what's called the electromagnetic spectrum. And you may have heard of this before. it essentially refers to the phenomena that all light and all things around us emit and absorb electromagnetic radiation, right? We see only a very, very small part of the electromagnetic spectrum, which consists of different wavelengths of light and energy. You will see this image is showing the full electromagnetic spectrum, ranging from gamma rays being very um, small wavelength to radio waves being really long wavelength. And some of these, channels or ranges in the electromagnetic spectrum might look pretty familiar to you. We use some of these frequencies to heat up food in the microwave. We use them to transmit radio waves and Wi-Fi and internet signals to your phone and so on. So this is stuff that kind of goes unseen sometimes, and we take it for granted. But pretty amazing what we can do by understanding and leveraging the electromagnetic spectrum for communications and for remote sensing. So key things here: we see a very small part of the electromagnetic spectrum, and we can transmit and receive these electromagnetic waves using devices like cell phones, satellites, and GPS units. So, which parts of the spectrum do we see? You may know that we see in red, blue, and green. Red, green, and blue. Our eyes have three cones or receptors, photoreceptors, that are able to essentially separate those different colors. If you have a furry friend at home, you may have noticed that when you throw the ball for Spot, Spot doesn't always do as good of a job being able to track it or find it after it's been thrown. And that's because dogs only have two cones or photoreceptors, and so their vision is not as rich as ours, since we have three. And other critters actually have different numbers of cones and photoreceptors. My favorite little story about this is the mantis shrimp, which is a sea creature. It has 12 photoreceptors in its eyes, so we cannot physically imagine the images that the mantis shrimp is able to see. There is a much broader spectrum of colors and a richer spectrum of colors that these creatures can view with their 12 photoreceptors, relative to our puny 3 photoreceptors. And if you want to learn more about this, there's an amazing podcast from Radio Lab about the mantis shrimp not only being an incredible kind of remote sensing capable organism, but being able to do pretty incredible physical feats, including breaking the barrier of sound as it uses its claw to stun its prey underwater. So, highly recommend that, and geeking out a little bit on the electromagnetic spectrum as it relates to our friend the mantis shrimp. So, okay, we have all of these different electromagnetic wavelengths. We can observe different parts of the electromagnetic spectrum. The key insight in remote sensing is that different materials or different objects have different properties that we can observe by looking at the electromagnetic spectrum for those objects, right? For instance, if we look at the wavelengths of light that are reflected by vegetation, so this little green box here, by buildings, little red circle, and by water, the blue circle, we can see that each of these three materials reflect quite different wavelengths of light. So this plot on the right-hand side is showing the reflected light on the y-axis and the wavelength on the x-axis. So the same x-axis essentially as this, our previous plot. But the key insight here, each of these materials reflects light differently. And this makes sense if you just take a step back and think about it, right? Vegetation is green. It reflects green wavelengths of light. Water scatters light, so it does not actually reflect that much of any wavelength, and this scattering often causes it to appear blue. Buildings might reflect red wavelengths of light. Certainly, they look different to our eyes than vegetation. So, because of these, what are called spectral differences, or differences in the electromagnetic spectrum that these objects reflect, we can actually learn a lot about what materials or objects might be in an image just by observing the electromagnetic spectrum and which wavelengths are reflected in a given image. So when you look at an image, that's all you're seeing is the light that was reflected in a number of different wavelengths, and for our eyes, we see in red, green, and blue. So the key insight, remote sensing, different materials and different objects reflect different parts of the electromagnetic spectrum. And, we just rigorously defined some of these properties that we are interested in when we look at remote sensing data. But, just looking at some of these images gives us a sense of how much information they really contain and how rich that information really is. So here I'm showing an image of California from October 2023, and then I'm going to jump forward by about 6 months and show you the same exact image, but just in March. So look at the stark difference between these two images taken in March and October. What are some of the things that pop out to us? I encourage you to pause the video and maybe flip back and forth yourself a few times and think about what are some of the key differences that we see. And I'll go through some of my observations. I'll give you a second to pause and ponder if you like. So what do we notice about the differences between these two satellite images of California between March and October? And we're not going to get technical and talk about the electromagnetic spectrum. Let's just talk about what some of the differences in the landscape are. Well, the first thing that pops out at me is all of the snow in the mountains, right? The Sierra Nevada are totally covered in March 2024 in snow. You got some snow up here on the Coast Range too, and in the Cascades. So a lot of snow. Very big difference in between October and March that we can start to observe and even put some numbers around by using some of this satellite data. For instance, you could think about how many pixels changed from not covered in snow to covered in snow between this image and the next. The second thing that jumps out at me is the vegetation changes, particularly in the Central Valley and the kind of rim around the Central Valley, which is quite dry in October and quite brown in terms of the color. But if we flip to March, you can see a pretty vibrant green kind of encasing the whole Central Valley due to the growth of vegetation that is reflecting the green lights. So again, you could think about doing this kind of change detection analysis in which you could think about all of the pixels that previously didn't have vegetation and now do. And we'll learn in a future lecture and tutorial about how we can use what are called spectral indices in order to measure changes in vegetation from one time to the next. Anything else jump out at you here? There's one more thing that I want to point out, and it's clouds, right? The cloud cover. There's not a lot of clouds close to the shore on this October image, and kind of a front of clouds coming in March. And so lots of differences that we can pick up with our human brains just looking at these two images. Similarly, we looked at some recent infrared imagery describing the pre and post fire reflectance in infrared wavelengths due to the recent Palisades and Eaton fires. And you can see just by flipping back and forth, the reflectance values in these two areas changes quite a bit between the pre-fire and the post-fire images. And again, we can use this information to do things like estimate the burned area, not only the areas, but the severity of the burn taking place in areas. And that's research that is ongoing with a group that I'm involved with here at Cal Poly, led by Stuart Wilson and by lots of other researchers in California who are trying to develop new ways to do this burned area mapping and burn severity mapping. So just another example of the power of remote sensing data and what we can do with change detection analysis. So great, let's talk a little bit about bands or channels in remote sensing. And these are essentially the electromagnetic wavelengths for the data that we collect. So I mentioned that we see in red, green, and blue channels, our eyes have photoreceptors that are aligned along the red, green, and blue wavelengths. And so when we put those together, we get what is called a true color image, like the one on the right-hand side of the screen of Cal Poly. So, like I said, we need 3 channels to form this image, red, green, and blue, and they're kind of given, the rough areas are given on this little visible spectrum plot by these white bars. Those are where in the electromagnetic spectrum each of those channels is coming from. Great. So we can also isolate each of those bands or channels, right? So we can isolate the blue channel out of the true color image. It's between about 45 and 52 microns, or micrometers. That's what this little symbol means. Very small distance. And we can use this wavelength to detect a number of things, most of which reflect blue light. Things like water, clouds, snow, and aerosols. And if you look in this image, and I just flip back and forth between the true color and the blue color image, what are the things that really pop in the blue image at Cal Poly? They are the buildings with white roofs. In fact, this is our building right here that we are usually in. Really pops out in the blue channel remote sensing data. And then we've also got some really dark areas right here. What are those? Oh, swimming pools. That makes a lot of sense. So blue, the blue band, very useful for detecting things that are white and blue, things like water clouds, snow, and aerosols. And there you have it. We demonstrated it on Cal Poly. Moving along, the green band, right? What do you think this might be useful for? Well, green things, right? Vegetation dynamics, plant health, algal blooms. And again, I'm going to flip back and forth between the true color image and the green image. And you can see that some of the green areas of vegetation kind of pop in the green image, right? We've got some vegetation on the hillsides here, lighting up, some riparian corridors. I think the lawn, Dexter lawn, is really popping. It's probably irrigated and quite green. We got some trees, I think part of the orchard right here. The baseball fields lighting up, especially the grass parts. So these green wavelengths, super useful for understanding vegetation dynamics, and we'll see that in one of our tutorials. Moving along to the red band, about 63 to 69 microns, and I should just mention the green band is about 52 to 60 microns. The red band, useful for detecting things like soil, buildings, roads, and pavement. Also useful for understanding chlorophyll absorption in plants. So plants are actually sensitive to this portion of the electromagnetic spectrum as well. as they uptake chlorophyll, and we can use some of that in order to understand plant dynamics, and we'll see how in one of our future tutorials. And if you compare some of the red imagery, the red band imagery, one of the interesting things we can see is the red objects kind of lighting up. For instance, look at the track over here and the red colored the place where you run, right? Like where you run around the track, the asphalt, and these red buildings right here and right here. Let's flip to the red image and see what those look like. And yeah, they're really popping out. They're quite dark, especially relative to some of the other images. If you look at the track, it's popping out in the red image, but not really in the green or the blue. So another example that this stuff really works. So those are the channels that we can see with our eyes, right? Red, green, and blue. But there's a whole big electromagnetic spectrum out there. And we can actually measure reflected light in areas that we can't see. So this area of the electromagnetic spectrum is called the near infrared band. And it is slightly outside of the visible range of wavelengths that we can see. It's 0.77 to zero point 0.9 microns, and this is useful for detecting biomass, for detecting boundaries between things. So in this near infrared channel, you can see the baseball fields really pop out. So again, by combining some of the information in each of these channels, we may be able to increase our confidence about detecting objects or changes in objects. So that's the NIR, or near infrared channel. Now, what we can also do that is quite interesting and visually very interesting is combine some of these channels that are not in the visible range of lights that we can see, and we can put them in the true color configuration and create what is essentially called a false color image. So now, instead of red, green, and blue light, I am making this image with near infrared, green, and red light. And you can see it looks pretty different than an image we're used to seeing. Like the trees are now red, the track is now purple, some of the buildings are still white, the grass on the baseball fields is now red. And this configuration, as you may have surmised, is pretty useful for detecting trees and vegetation, right? They really pop out as this red color. So if you're a GIS analyst looking into vegetation dynamics, this is a pretty common wavelength or band false color combination of bands that you could use to explore vegetation and tree dynamics. So, like I just said, visible light is only a small part of the electromagnetic spectrum, and we can also transmit and measure radiation outside of the visible spectrum. I just showed you some data from the infrared channel. And we can use that information in the similar way that we would use visible information to understand material properties and objects that we're observing. So, what we just talked about is only one type of remote sensing, which is essentially taking photos of things, or radiometric remote sensing. There are a few different types of remote sensing that we can also use to understand processes and learn about the Earth. And I'm just going to introduce some of the cool ones right now. And these are probably the most common ones that you are likely to encounter in your day-to-day lives and scholastic and professional careers. So we just talked about the radiometric or optical method of remote sensing. This is the one that we're going to use in class. This is the really common things that we're used to looking at. Pictures, right? Photos. We record the reflected light at different wavelengths, and then we can process or combine those reflections in different ways to understand different processes. Some examples are our eyes or cameras or the satellites that take pictures. You may have heard of radar. Radar means radio detection and ranging. It's sort of an acronym. Uh, the RA is kind of the radio part. It was invented in World War II to track the positions of aircraft. So but we have been able to repurpose that original technology and use it for lots of interesting things with great applications in the earth science field. The way that it works, essentially, you shoot radio waves at things, and a quick reminder, they are one of the longer frequency, sorry, yes, lower frequency, longer wavelength parts of the electromagnetic spectrum, right? They are invisible to our eyes, they pass right through us. They are essentially what we use to transmit data from our cell phones to the internet satellites and back. But the way that these things can tell us useful information that we want to know is you shoot these long wavelength radio waves at things. We know that these radio waves travel at the speed of light, right? All electromagnetic radiation does. And then we listen for the radio waves to come back to us. And based on that time that it took for a radio wave to be emitted from a transmitter, go and bounce off of something and come back to that same transmitter, we can essentially measure a distance, right? Because the time it takes for the radio wave to go and bounce off of something and come back, we know that it's traveling at the speed of light. We know the time it took. So we can essentially figure out a distance by dividing that time by the speed of light, right? And so if we know that something took a second to travel to an object and bounce back to us, and we know that it is the speed at which it's traveling, if we essentially divide the time by 2, we know that the distance that the object away from us is proportional to the time that it took to travel there and back. So that's essentially how the cops can get you a speeding ticket, right? They have a little radar gun. It shoots radio waves at your car. They bounce off of your car and bounce back. This happens lots of times within the span of 1 second. And based on the differences in the position of your car, you can calculate a velocity. So these are super useful for figuring out how quickly weather fronts are moving. So weather radars are a very common instrument, and satellite weather radars, but also ground-based weather radars can tell us essentially how quickly the clouds are moving, how far they are away from the weather stations shooting the radar waves, and how fast they're moving. And I'll also mention there are very interesting and cool radar satellites called synthetic aperture radars that we're going to talk about towards the end of this lecture series that can actually map changes in Earth's elevation due to things like earthquakes, landslides, other factors that alter the Earth's surface and changes in the Earth's surface, things like melting ice sheets. You may have heard about sinking ground in California due to groundwater pumping. We can measure changes in the land surface elevation by shooting radio waves from satellites at those areas over time and measuring changes in the distances between the ground surface and the satellites. So radar, suffice it to say, we shoot radio waves at things, we listen for how long they take to travel back to us. Since we know the speed of light, we can map how far the objects are away from us. By doing this over time, we can understand changes in the position of the objects, and the objects can be weather fronts, they can be cars traveling towards us, they can be the ground surface changing due to a landslide or an earthquake. So that's radar technology. A similar remote sensing technology is called LiDAR. That stands for light detection and ranging. It's very similar to how radar works, except instead of shooting radio waves, you shoot photons at things and measure how long it takes them to come back. So, this is the technology that self driving cars use in order to map out the environment around them and hopefully not crash into things. Um, we can also do very high resolution topography mapping using this kind of technology mounted on airplanes and satellites and produce images like the one that we're seeing in the bottom left corner of a volcanic caldera. Now, look at the animation on the top right of the screen. That is essentially how a LiDAR works. It is rotating around this room. The room is shown kind of from a bird's eye view, top down in the center animation. And then the bottom animation is showing, again, from the top down view, how the LiDAR is able to see the objects in that room. The red line here is the photons that the LiDAR is shooting, and then, again, measuring the time it takes to come back to the sensor. And by doing this, you can figure out the distance to objects in the field of view. And so that is how a LiDAR works. Very similar to a radar, except we use photons instead of radio waves. And very exciting, this technology is gaining momentum and is becoming much cheaper to implement. It is now in the 3 most recent iPhones and several versions of Android models, and becoming pretty useful for doing things like scanning objects and creating 3D models of them, again, which we will experiment with later in this class. So that's LiDAR. Another different remote sensing method is called geodesy, and that includes GPS, global positioning systems, and gravity metrics, gravity measurements of Earth's gravitational field. And this is a pretty broad area of remote sensing. In fact, it's kind of a whole subfield of Earth sciences called geodesy, which refers to measuring changes in position or gravity, or just measuring the position or gravity in the position of Earth very precisely. And this is essentially GPS, right? Like, how does GPS work? We'll get into that, but GPS devices are considered geodetic devices. You could use this technology to understand things like changes in the Earth's surface, deformation due to faulting, earthquakes, groundwater extraction, changes in Earth's mass or distribution of Earth's mass, things like melting glaciers, changes in mass due to mines or mineral extraction or dams, things like that. So this rotating sphere on the right-hand side is actually showing Earth's non-uniform gravitational field, right? Earth has different gravity at different points on the Earth's surface. And if you think about this a little bit, it kind of makes sense. You can see a big positive gravity anomaly in the western US where the Rocky Mountains are. Similarly, you can see a big positive gravity anomaly in Greenland where we have big ice sheets up here. Also, the Andes Mountains and the Himalaya Mountains pop out clear as day as being places where Earth's gravity field is larger than other places. And we'll talk about some of the satellites and techniques that we can use to measure this in subsequent classes. But suffice it to say for now that one whole field of remote sensing and geospatial sciences is called geodesy, and we use these essentially gravimeters that can measure Earth's gravity or changes in Earth's gravity, and GPS devices which measure position or changes in position, to understand some of these processes that are causing changes in Earth's mass and surface deformation. Quick word on GPS, since we just mentioned it and it's important to kind of build up the intuition for how it works. essentially, this animation sums it up. The way that GPS works is through a technique called triangulation. And what that means is by being able to record the distance between your GPS device and at least three satellites, you can essentially triangulate the true position of a GPS device by just those three pieces of information. And this example is basically showing how it works and using all of the satellites that are within the field of view of the hypothetical GPS device and highlighting them in red. So the GPS device on Earth's surface is kind of shown as a red dot there. All the satellites that are within view that it can use to measure its location or triangulate its location are highlighted in red, and that changes over time. So you can see that as the Earth moves, as the satellites rotate, you have a different number of visible satellites at any given point in time, which will affect your ability to accurately measure position on the surface of the Earth. You've probably seen or worked with a GPS device. This is kind of what it looks like, although you probably are more familiar with your phone at this point. And quick word on some of these GPS, processes and systems that are in place. It's fairly remarkable that we have all this machinery set up that we can do this. We have a 24 satellite constellation, which gives us about a 5 or 10 meter accuracy for civilian grade GPS right now, which is fairly just mind boggling that we can even do that. No matter where you are on the Earth, you can know where you're at within 5 or 10 meters precision. There are ground monitoring stations to track these satellites. There's a master control station in Colorado, and this is very, very cool technology. Initially used for military purposes to track intercontinental ballistic missiles, and thankfully, we've repurposed some of those technologies for other applications. Like I said, it works with trilateration or triangulation, and basically you need at least three known locations, which are the satellites, in order to triangulate or calculate a position on Earth's surface. And we'll go into a little more depth about how this works. There's a really nice external resource that I will walk you through. So that's GPS, which is a subset of geodesy. Moving right along through our tour of remote sensing methods, we have electromagnetic methods. Now, these are quite cutting edge and pretty interesting. Essentially, you measure changes in the electric or magnetic field and how those fields propagate through various materials in order to understand the composition of those materials. And so this little schematic on the left-hand side is showing how a airborne electromagnetic system mounted on a helicopter kind of works. It induces these currents into the subsurface, and then it measures the decay in the electric or magnetic field that is emitted by those materials. And based on the nature of that decay, you can say something about what those materials might be. For instance, we know that water conducts electricity. So if you have a very strong reflector in the subsurface of your electromagnetic signals, maybe there's some water down there. Similarly, we know that clay minerals are susceptible to electrostatic charges, whereas gravel and other larger rocks are not. So by observing the property of electrical resistivity in the subsurface, we can determine what's down there. Are there sands? Are there gravels? Are there clay minerals? Are there mineral deposits? Are there other precious metals. Very interesting technology that can be used to explore the subsurface and the materials down there. And it's currently being used here in California by the Department of Water Resources and other groups to map subsurface aquifers and groundwater resources in the Central Valley and also the Salinas Valley. So the image on the right is actually showing the hydrogeology of an area in the southern Central Valley based on this electromagnetic data acquired from helicopters, and also showing some interpretation for what kind of geologic materials and hydrogeologic features are present. So, in addition to the techniques that we have talked about, we can also do what's called stereo imaging or photogrammetry. And this is pretty cool. By imaging the same object from different angles, we can actually estimate the structure or the geometry of that object, right? And if you think about why our eyes, like why we have two eyes instead of one, it's so that we can sense depth, right? Have you ever tried to catch a ball with closing one eye? It is way harder. I suggest you try it. If you have a pen, if you're taking some notes, and you want to just toss your pen up and down and catch it in your hand, try doing it with one eye and see how much harder it becomes. And that's because our sense of depth and three-dimensional space is derived from our ability to image the same object from two different angles, being our eyes. Have you noticed that your smartphones now all have more than one camera? And it's for this exact reason, to understand the depth of an image from two vantage points rather than just one. And so when you know the positions that you are taking photos of an image from, and you do this over and over and over again, you can create three-dimensional models like the one that I'm showing in the animation in the right-hand side, based on these multi-angled images. And this process is called photogrammetry. And it's super exciting and super cool technique that we can use to do quite useful, essentially topographic mapping and elevation mapping of not only the land surface, but features on the land surface, things like trees, vegetation, structures, and so on. So this is actually really commonly used in like surveying real estate. Like if you ever take a virtual tour of a house or a property, probably photogrammetry may have been used in that. So, awesome. We just talked about 6 of the key types of remote sensing, and we talked about how each of them works, the physical principles on which they're based, and some of the things that they can let us do. But I also want to talk about the applications in earth sciences associated with each of these techniques, and like why do we care, right? Because all this stuff is cool to nerd out on, but really what we care about is doing useful things with these technologies. So the first kind of disambiguation or difference between some of the technologies that we talked about is this difference between passive and active remote sensing devices. The key difference here, and it's very simple, is that passive sensors just record data. They just take a snapshot of the reflected light at a given point in time, right? Like a camera without a flash is a passive sensor. You're just capturing at one point in time the reflected radiation, electromagnetic radiation, reflected from the sun, right? So the sun is kind of our energy source. That light energy bounces off things. The intensity at which it bounces off is recorded by our camera. And we don't have to emit anything, right? The sun is our emitter of light. Contrast that with something like a radar. in which you actually have to emit the signal and then listen for the echo back, right? Same thing with a LiDAR, where you emit a photon and listen for it to come back, or a sonar, right? How underwater submarines map their positions and locations of other objects. Those are called active sensors, and that they're active because they emit something, a signal, and then listen for the response, as opposed to the passive case, where essentially the sun is our signal emitter. Now, we can put remote sensing devices on lots of things. We can put them on phones, drones, planes, and satellites. And there's kind of important considerations for each of those devices and data acquisition platforms, right? The first is spatial resolution, right? The size, the real world size of a pixel, which dictates essentially how well we can characterize individual objects in an image, right? So if we have a spatial resolution of, for example, 30 meters, which means that one side of a pixel is 30 meters length, and the other side of a pixel is also 30 meters length, so a pixel would be 900 square meters in area. And that's a very common spatial resolution, 30 meters for NASA's satellites. But if we have a 30-meter resolution pixel, we can't expect to be able to pick out cars in our remote sensing images, right? Because they are smaller than 30 meters. So how can we expect to reconcile an object that is smaller than kind of the smallest pixel size that we have, right? We need objects in our data. If we have any hope of identifying objects in our remote sensing data, they have to be bigger than 1 pixel. So if you think about this, if you put the same sensor on a phone and then take a picture of an object, you're going to get a different spatial resolution for that object being 10 feet away from it than you are if you were taking that same picture from an airplane that was, a mile or two away, right? Your picture from your phone taken much closer is going to have a much higher spatial resolution. And as we keep going further and further away from an object, we get a lower and lower spatial resolution and a grainier and grainier image, right? So that's an important consideration. But at the same time, we can't take a picture of everything, from 10 feet away everywhere on Earth every day. But we can have satellites that orbit overhead and take a very, a lower resolution picture of a very large portion of the Earth's surface. So we're kind of trading off this spatial resolution for coverage, right? So we can accept a lower spatial resolution if we can get information about a very large area. That seems like a good trade-off to make. For instance, maybe we want to understand the weather in the United States as opposed to how many cars are parked at Cal Poly right now. And a lower resolution and larger coverage data set would be much more useful for understanding something at the country or continental level. So it all depends on what you're trying to do and where. And this resolution coverage trade-off is kind of a fundamental limitation in remote sensing that we always have to be thinking about. So at the sort of lower resolution, higher coverage side of things, we have our satellites, right? Our satellite data collecting this information all the time. These are very highly scalable, high coverage data sets, right? They're orbiting the Earth. They're providing new information like all the time, 24/7. Some satellites can image the same place on Earth multiple times a day at spatial resolutions of about 250 meters. Not bad, pretty remarkable that that's even possible. So, very, very good coverage, free data, very, very scalable as far as global and continental analyses, but it's not always a great spatial resolution for detecting very small objects. These satellites are acquiring enormous volumes of data, so much, in fact, that our human eyes and brains are not really even able to look through them anymore. We need to leverage computers to do the number crunching and data analysis on these volumes of data. And that's why it's quite an exciting time to be involved in remote sensing right now. And there are so many applications of these data in natural resource management and earth sciences, and I'm going to step through 5 of them, but there are more. So, water resources, forestry and fire, ag, natural hazards, and energy, just to name a few. In water resources, you can think about flood and drought mapping, right? We just looked at some of the coverage that you can get in these remote sensing data sets. So you can think about mapping flooded areas, the day of the flood or the day after, and charting disaster and emergency supplies to, travel to the most affected areas. So, we can also do things like estimating components of the water cycle. We talked about the snow covered area using the remote sensing maps that I showed earlier. But we can also use radars to do things like measure the rainfall and the snowpack in various areas. We can build models to measure evaporation and evapotranspiration, which is pretty remarkable and very useful for thinking about hydrologic cycling. Evapotranspiration is the water emitted to the atmosphere by plants and by the bare evaporation of water from the ground surface and the transpiration of water through the roots and pores and stomata of plants. So, very important for hydrologic applications, understanding crop growth, crop phenology, crop yields, and then, of course, forecasting, weather prediction, and extreme weather. Very useful application for remote sensing and hydrology. Forestry and fire. You have probably already seen land cover maps, vegetation maps, vegetation phenology maps, right? Like how are the vegetation changing over time in an area? We looked at some of the differences in vegetation between an image in October and April. That's a good example. We can map deforestation, reforestation, fire extent, and severity. We can do things like map the canopy height using LiDARs, which is super exciting, right? These LiDARs, we can put them on satellites, shoot photons at Earth from satellites. Some of them bounce off of the treetops, others bounce off of the ground surface. And by differencing those two photon returns, we can actually estimate the height of a tree canopy from lasers in space. Truly remarkable. And we can derive other interesting things like fuel loads and moisture status from remote sensing, which are, again, important in forestry and fire. Natural hazards, we all already kind of mentioned this, but forecasting and mapping hurricanes, earthquakes, tsunamis, floods, fires, droughts, and landslides. This is like lots of the fuel for the GIS in the news segment of our class. But then there's also kind of an emergency response angle here, right? Like GPS devices, response routes, evacuation routes, like optimizing search and rescue, evacuation, I already said. But there's a huge, I think, unrealized opportunity to leverage geospatial technology and remote sensing in response, in the disaster response and planning part of natural resources and natural hazards. Agriculture, right? This makes a lot of sense. We can monitor crops, we can monitor nutrient uptake. The Some of the wavelengths in the electromagnetic spectrum that I mentioned earlier are actually sensitive to chlorophyll and chlorophyll uptake. So you can say, oh, these plants are uptaking their fertilizer and nutrients efficiently or not. Same thing with water use. Evapotranspiration we can measure from plants. We need water to grow plants, right? So all of the factors integral for understanding the hydrology are also playing a role here in agriculture. We can map crop types, changes in cropping patterns, and so much more. Forecast yields, all sorts of useful things. in the realm of agriculture. And energy, right? Well, agriculture actually is kind of a big part of energy, especially if you know about the renewable fuel standard and the role that corn can play in ethanol, and ethanol can play in gas and petroleum production. Um, but besides that, there are lots of interesting applications for remote sensing in energy. For instance, you can, figure out where it's sunny. We can look at the cloud cover dynamics in different areas over time, right? Like you want to put solar arrays where it's not cloudy. And so we can find those locations by looking at remote sensing data. We can look at the topography and the river flow where we might want to put dams for hydropower. Um, you can also think about where you might put something like a wind turbine based on topography, based on wind patterns. Um, and then also collecting weather data for optimizing our electricity grid and power generation due to demand forecasting and fulfillment. So, several areas where remote sensing technology is being pretty useful in energy. Quick recap, we talked about 6 types of remote sensing today. Um, they are, in addition to the optical and radiometric methods that we've been looking at, which are basically just taking pictures of things, they are radars, lidars, electromagnetic methods, geodetic methods, and stereo and photogrammetry. We talked about some of the important applications where those technologies are being used to do real and important work in real applied contexts. And I also talked about some of the new and emerging technologies that are accelerating our progress here and some of the exciting things that are just kind of taking shape. Two of the ones that I'm really excited about are the airborne electromagnetic surveys of groundwater systems in California and the LiDAR based mapping of tree canopy heights from space, literally using space lasers, that is now available globally. Super exciting stuff. As we look to the future of remote sensing, I have identified a number of different themes that I want to highlight to set the table for what the future might hold. The first is better and cheaper sensor technology. We have, I just mentioned it, new types of LiDARs and radars on satellites collecting data. There's a new radar satellite called NISAR, the NASA Indian Space Agency collaboration synthetic aperture radar satellite, NISAR, NISAR. It just got launched last year. There is another one called the Surface Water Ocean Topography satellite that's going to let us measure the heights of rivers, which is pretty novel. Never before have we been able to do that. I did an interview in Newsweek a couple of years ago about this technology that was pretty fun. Some other new technologies. We have new LiDAR devices rolling out in phones. We also have what's called a dual frequency GPS coming on new phone models with a 1 meter accuracy, which is totally bonkers to be able to measure your positional accuracy on Earth's surface with 1 meter accuracy and precision. Just kind of insane if you think about it. And then drone technology, which we haven't talked about too much, but all of the sensors I showed, you can basically put them on phones, drones, planes, or satellites. So very relevant here, especially if you need high spatial resolution data for something. The costs for drones and research grade high quality drones is coming down a lot, which is really opening up their utility as a tool. Here are some of the satellites that I just mentioned. Super excited about all of them. Now, moving along, open source software is really catalyzing remote sensing technology development and letting people wield and process some of the remote sensing data in new and novel ways, like we've never really been able to do before. without sophisticated and, often enterprise level tools. So this is some data that I created, a three-dimensional model using my cell phone and about 2 minutes of images acquired around these Joshua trees. And there's an open source tool called Polycam that lets you create three-dimensional models like this, and you can explore the accuracy and utility for various applications. So this was not hard to do. You could probably do it too in about 5 minutes. So this is not the only open source software tool that's being used effectively. There's lots more that are just as exciting, and makes it an exciting time to be doing this kind of work. Here's another three-dimensional model processed with open source software. Images were acquired using a drone this time, so covering a much larger area. But what a cool image of some of the Rocky Mountains and the topography. Truly amazing that this was able to be made for free. There's also a very, very cool remote sensing coding platform called Google Earth Engine. And this essentially is a way to access for free all of the remote sensing data collected by NASA, like ever, since the 1970s. With just a few lines of code, you can essentially leverage Google's cloud compute resources to process 30 years or more of satellite data and do things like make time series plots of things that we care about, all for free. And I use this tool in my research a lot. It's frankly amazing that it exists. And before, doing that kind of analysis was so difficult and painstaking and basically required a computer science degree. But now with these open source tools, we can really leverage massive amounts of these remote sensing data to solve real problems and do interesting science. Gen AI. You guys are probably using Gen AI in this class. You're probably using it in your lives. Gen AI is coming for remote sensing data. We are going to live in a world where you can open up a Gen AI GIS and you can type, "Make me a map of SLO County," and highlight the vegetation areas. And it will just do it for you, and it will be pretty accurate. And I will demo some of the emerging tools that are starting to do these things in later lectures. But here's a good example where I'm leveraging a Gen AI model called Segment Anything. And it's a little hard to see, but I'm inputting a little prompt. That's just a word here. I just input building into the prompt, and I'm going to click segment. And it does a pretty good job, you will see, finding the buildings in this satellite image. I'm going to show again the same example for a tree. And I clicked segment, and it's going to do a pretty damn good job finding the trees and in this image. And this is an image of Cal Poly. But this is amazing, right? Like, the computer is decoding the meaning of tree and building and figuring out on the fly the pixels, essentially, which contain those objects. And that is all being done in a fraction of a second by a generative AI model. And this is, frankly, it's amazing. We've never been able to do stuff like this until the very recent past. Another exciting area of research is around data fusion in space and time. So combining data from different sensors with different spatial resolutions acquired at different times and combining them in fancy and new ways in order to form new data that is actually more useful than each of the data sources were beforehand, right? So combining things that are actually more useful than just the sum of their parts. And there's a lot of exciting research being done here. I'm not going to talk too much about it, but essentially, it has been shown that by conditioning some low resolution data on higher resolution data, you may be able to resample the low resolution data to be reflective of the high resolution conditions, even if you don't have high resolution data for a single date, which could unlock some pretty interesting applications, but more to be done on the research side, I think. Finally, AR and VR to measure and visualize the natural environment. There are lots of advances on mobile phones being leveraged currently to monitor, model, and monetize aspects of these technologies. So here I'm showing a phone application that uses computer vision and some of the sensor technology that I talked about that lets anybody essentially measure the heights and the diameters of trees. This is a tree that I measured on Higuera Street by the Mission. And yeah, this was not possible before the last few years and before these technologies made it onto our everyday devices. And these are improving operational efficiencies and, you know, allowing us to collect this geospatial data, look at these maps in ways that are faster and more accessible than before. So just to sum it up there, lots of tailwinds for remote sensing technology in the geospatial arena. Better and cheaper sensor technology, open source software, generative AI, data fusion, and AR and VR are some of them. I'm sure we will see more in the next few years. And there's lots of clever things that we haven't even thought of yet. And maybe you can be one of the people who pushes some of these clever things forward and invents something that nobody has dreamed up just yet. I'll also just say there are lots of organizations developing and using this kind of technology. I have worked for a few of these companies listed right here. I'm just mousing over some of them. My wife has worked for one of them. A lot of these are doing good work in California. Some of them are probably big organizations that you've heard of, like National Oceanic and Atmospheric Administration, the UN, USDA, NASA, and so on. So lots of opportunities to get into this technology and get into these organizations using this technology. So finally, just a present-future comparison. Right now, we work on the desktop. We work with local data. We're limited by the processing power of the computer, and we work with one data set at a time. In the future, we're moving to the cloud. We're going to move our data to the cloud. We're going to use like armies of computers to process our data, and we're going to use lots of different data simultaneously to extract insights. So thanks for paying attention. Next time, we're going to talk about spectral indices and terrain analysis, also using remote sensing data. Take care.